because I had to process all the new vocabulary, which was wonderful. All of the new insights about meteorology, about weather, the connection between the atmosphere. And I also had to process while Elliot was really a leader on this really tight environment where there are captain vessel with people who have emotions and needs. So it's a really very interesting book. Whether you read it all in one fell swoop, or I think I've heard other people say they need to put it down and process what's coming in as a view. It's really a great book to read. When I told a friend of mine that I was coming to introduce Elliot to me, he said, "Oh, I just started this book, and there's a really good analogy that Elliot quotes. He quotes an astronaut saying that the depths or the width of the atmosphere is like the fuzz on a tennis ball." That's a really good analogy. And I'm sure that Elliot, when he was out on the high seas, the atmosphere felt a lot more than just fuzz on a tennis ball, but he certainly knew how to navigate weather, the sea below, the air above, the weather below, weather above. How do you navigate that, particularly in a changing climate? So that's what we're going to hear about tonight. And I'm delighted that you're here to do that for us.
All right.
Elliot.
Thank you so much.
You're welcome.
All right, very good. What could possibly go wrong? All right, well, first of all, I'd like to thank all of you for coming and for the very generous invitation to come down here and speak. I'm really flattered. I really look forward to speaking to you. Certainly answering any questions that I can. I've got a few slides to show you. You know, as well as being a mariner by trade, I've also found myself the last few years turning into a college professor. So I've learned to run on and plant slides and things like that as well. As well as learning how to plug in my computer to all sorts of different projectors. So I was ready, but the library was very accommodating with equipment. So anyway, right, I'm Elliot Rappaport, and live over in Surrey. And I guess by trade, I'm a professional mariner, and probably around here, some places that needs more explanation than others, right? But I've been, for most of my career, I've been a professional mariner, working mostly in sailing ships, sail training ships, and oceanographic research vessels. The last few years, I'm still spending some time at sea, but most of my time during the academic year,
You want me to turn it up so you can hear it?
Took a job about 4 years ago over in Castine on the faculty at Maine Maritime Academy. And I like to start with this slide just to sort of show, like, you know, just a sampling of the many things you can find yourself doing as a professional mariner, right? You can, you know, like me, you can sort of choose the slow anachronistic path, right? Sailing ships, but you can carry bulk cargoes. You can be in the tug and barge end of the industry. You can be on container ships. It's really just about limitless. And I also like to start out with this little number in the lower left-hand corner, 11 billion tons. What am I talking about there? Traffic. Yeah, so that is the average amount of traffic, exactly, the average number of shipping tonnage that transits the world's oceans each year, okay? And this is to sort of get the point across. You know, people think of seafaring as a very historic and traditional profession, and it is. But, you know, currently there, by whole orders of magnitude, there are more ships at sea, more mariners employed in the maritime industry, and certainly more, you know, more cargo, more goods being carried at sea than any time in human history. And this gives you the idea. In fact, we don't need ships anymore. We just walk from one to the next. Okay? So this is an image from a very interesting site called marinetraffic.com that provides real-time data from a technology called AIS, which is a transponder device that provides you know, position information from any ship, or at least any commercial ship that's underway at sea needs to carry one of these devices. And this is all collected. And this is actually from about a month ago, but if you took one today, it would look more or less the same.
Explain the color.
I can't. I always say, what do the colors mean? I always look it up, and I just forget. My wife is an engineer, and she says, why memorize what you can look up? So that's always the deal. I believe the green are just the commercial ships, different cargoes and different different types of ships. Okay, there we go. So so I wrote this book, and disclaimer, it's a book about weather, but I didn't really think of myself as an author until I kind of I found myself working on a book. And also, full disclaimer, I'm not really a meteorologist. I think, you know, as somebody said, you know, kind of think I'm sort of like a lot of mariners, right? I'm sort of an end user of weather, right? And, you know, so I have a vested interest in understanding weather, both from a day-to-day sense and also understanding the understanding meteorology as a science so you can make the best of the information that's being offered to you. But, you know, a science book inspired by the maritime learning environment. What do I mean by that? Well, it's, well, I start off sort of meaning, I feel like, you know, going to sea in the maritime industry is a tremendous sort of on-the-job learning workplace. I have a feeling a lot of workplaces are like that, but there's tremendous premium. You can go to a maritime academy and get a degree, but that's really a learner's permit, you know, for a long arc of training that really begins and continues throughout the time that you're at sea. And I think in part because of that, right, you know, most of us have had a successful career at sea, have done so thanks to, you know, a long series of partnerships with people who are really skilled at what they do and good at explaining stuff. So there's a really, really valued tradition of on-the-job training and just verbal sharing of information. So, you know, I got very interested in just sort of explaining things, you know, having things explained and also thinking about, you know, worthwhile, effective, and efficient explanations for other people that I was working with. And I got particularly interested in weather and actually sort of began developing, you know, mostly for sharing within the training environment, some written information, you know, short chapters and essays and things like that on weather. Because what I found is there weren't really a lot of books. There are a lot of textbooks and things like that. And then there were like perfect storm adventure stories. But I really felt like there was kind of a middle ground where, you know, at least as far as I could tell, there was still a need for a, you know, a weather book where the science was correct that was sort of written in plain language. And it sounds like, you know, if you had to read my book, you read a chapter and then put it down and take deep breaths for a while. Maybe I didn't quite achieve that objective, but that's what I was aiming for anyway. So what I want to talk about today is some sort of fundamental explanations of weather, some of which you'll find in the book also, and kind of in parallel with that, just to talk about yeah, global weather systems, which are really anchored by the same principles. Weather kind of happens, whatever scale you're looking on. The principles are pretty much the same, and sort of historical sailing routes. So how human populations, there was a question a minute ago about shipping routes, right? And certainly historically, human populations have spread themselves around the globe in a pattern that has a lot to do with the way the wind blows. So we'll talk a little bit about that. Since, you know, one theme for tonight is climate, right? I'm also not a climatologist, and honestly, as a mariner, you kind of, you know, it's very much a one day at a time sort of occupation. So, you know, you can observe weather, but, you know, difficult to draw a line through it all and draw, you know, scientific conclusions. That's what the scientists are for, right? You know, draw scientific conclusions about whether or not you're seeing something that is the effect of changing climate. But that said, there are some very definite implications in terms of global weather systems and marine navigation, you know, connected to the warming climate. And there's definitely stuff going on that is a part of that. So I'll try to talk about that as well. So why weather? If we don't think about, like, you know, weather is a three-legged stool, right? Here's what I'm going to try. Okay, I'm going to say that, you know, looking at the fundamental principles of weather, it really has to do with when the weather happens in the atmosphere. And the reason that it occurs is that the Earth doesn't receive energy at an equal rate from the sun. The poles are colder, right? And the tropics are warmer. And because of that, weather is really just a process that's, you know, that's there to attempt to equalize that difference in thermal energy on the surface of the planet. Weather, at least weather on Earth, is heavily coupled to the fact that most of the surface of the planet is covered with water. The cycling of water back and forth, the evaporation of water, mostly from the oceans up into the atmosphere, and then, you know, its eventual condensation and return to the surface as snow or rain, has a major role in moving thermal energy around in the atmosphere. And then finally, the whole world is turning, right? So if if the Earth wasn't a rotating planet, if it was just a fixed sphere or a cylinder or something like that, things would look a lot different. I'm not sure exactly how they look, but they look a lot different from the way they do now. So, but first, right here is that quote, right? Weather happens in the atmosphere, and in fact, you know, it's a little hard to say exactly how thick the atmosphere is, but, you know, say around 100 miles. But actually, weather actually happens in a layer of the atmosphere that's very, very close to the surface, something called the troposphere, which is we're about 90% of the atmosphere by mass. So all the molecular material of the atmosphere, nearly all of it, is all within, you know, really not much more than 10 miles, and in some cases much closer than that to the surface. So it's really like I say, there's this quote, right? I was very captivated by this the first time. I'm old enough to remember reading this in the newspaper and thinking, wow, that's, it's observed from space. Not that I've ever been there, right? But you can see right here in the atmosphere, it's really just, it's like, just a very, very thin membrane. It looks a whole lot thicker than this when you're standing on the surface looking up. But in fact, it's a very, very thin layer of gas. It's mostly nitrogen. There's some oxygen there, very, very small amount of carbon dioxide, although too much as we're learning. And water vapor also, the gaseous form of water. That's most of what's in the atmosphere, but that's really where weather occurs. So the Earth is absorbing energy constantly from solar radiation. And actually, interesting fun fact: it's actually the Earth absorbs energy from the sun and then heats the atmosphere from below. We get long wave energy from the sun. The sphere of the Earth absorbs that energy and then re-radiates it as infrared energy, also known as heat, right? But in any case, the amount of energy that's reaching the Earth from the sun is not really equal by latitude. If you think about solar rays like as the beam of a flashlight, near the tropics, they meet the atmosphere at more of a right angle and spread out over a smaller area, or near the poles, right, the same shaft of sunlight is going to spread out over a larger surface area. So you're getting, less, I guess it would be photons, right, particles of light, but you're getting less light per square meter or mile near the poles than you are at the tropics. So, it's also traveling at a shallower angle, so less of it actually gets to the surface, more of it's reflected. So the poles, take-home method, right? The poles are much colder, the tropics are warmer, and that's actually exaggerated by the fact that seasonally, right, our axis is tilted. The Earth's axis, it turns out, is tilted to the plane of its orbit. So over the course of a year, right, again, most of us know this, right, but over the course of the year, as we make a circuit of the sun, seasonally, the amount of energy each hemisphere gets from the sun is going to change. So the absorption in the tropics is pretty uniform across the year, but for a large part of the year in one hemisphere or another, the higher latitudes don't get as much energy. In some cases, they don't get any at all, right? In the polar regions, there's times of the year when there's really no solar radiation reaching the high latitudes at all. So those two things together make the tropics consistently very warm and the poles very cold. Okay, so sort of next fundamental, right, is this difference in density with air, really any substance. But as you say, the atmosphere is made up of gases, right? And if you cool a gas off, right, it becomes denser. If you warm a gas up, it takes up more space, it becomes less dense. And atmospheric circulation to start with is really, colder air tends to be more dense and sink. And as it does so, it displaces warm air. So warm air doesn't rise spontaneously, but it's more like it's pushed up by sinking cold air. And at the surface, that has a consequence, right? The surface where you have air that's sinking, the pressure, barometric pressure tends to rise. And places where air is being lifted or pushed up, the pressure tends to sink. And that rising air takes water vapor with it. And as that air rises, takes the water vapor with it. The air rises and cools as it does so, and typically that's how you get clouds, as that water vapor cools off, and you eventually get condensation. So clouds are formed by the condensation of water vapor into rain droplets or water droplets or ice crystals. So this is just another illustration of that. Water is evaporated off this first surface, mostly from the oceans. It's carried up into the atmosphere. And it moves around, right? This process called, transport, which is really just wind, right? Water vapor is carried around by the wind, and eventually it condenses into clouds. And if the clouds become dense enough, it settles back to the surface as precipitation finds its way eventually back to the oceans. So if we look at this we're going to sort of zoom out. We're at a hemispheric scale. Okay, so we're looking at a slice of, we'll say, the northern hemisphere. And if you think back to what I was saying a minute ago about how the tropics are much, much warmer than the poles. And what we're looking at here is actually the troposphere, right? This is this lower layer of the atmosphere. You can see the troposphere in the tropics, okay, is about it's about 55,000 feet tall. And then if you get to the poles, it's much thinner because the air is colder and denser. In the tropics where the air is the warmest and the least dense, it's sort of being continuously displaced by colder, denser air, making its way down from the higher latitudes. So you can think of like near the tropics, the air is the warmest and the least dense, and at the surface, the pressures are generally low, and the atmosphere here is generally very warm and moist. And you have sort of a continuous flow of air, cooler air from the tropics, from the higher latitudes towards the tropics. And then that air is lifted up and kind of flows back the other way. And so the weather in the tropics is characterized by this sort of continuous, relatively low pressure, warm, moist air, and lower surface pressures. And so this is tropics. We kind of look up where we are, right about halfway to the pole from the equator. Our weather is characterized by sort of cold air sinking at the poles and making its way further south and interacting with warmer air from the middle latitudes. So as that warm air meets the colder air along this feature called the polar front, okay, which is just kind of a continuous boundary between cold polar air and warmer air from the middle latitudes. The warmer air is lifted or pushed up by the colder air, and as it does so, again, remember we lift warm air up, it cools off, and we get precipitation, right? We get clouds and moisture. So that's the sort of constant stirring that's happening at the surface. We're getting air converging towards the equator, being lifted up, making its way sort of back towards the poles. And then again, at the surface, we have a feature where we have warm air that's flowing at the surface. Air sinks in the middle latitudes, sort of makes its way to the north also and bumps into colder air from the poles. Okay, so that's why we think about our weather here, right? It's sort of characterized by constant mixing of warm middle latitude air and cold polar air. What we're going to talk about a little more later on are these things called jet streams. And you can see, the atmosphere in each hemisphere. Roughly, you get these sort of three major changes in density. You get the tropics, which are very low density, and the troposphere is very tall here, we'll say. It's sort of in the middle latitudes, and then in the poles, okay, you get the area where the atmosphere is coldest and densest. And at these boundaries between the primary air masses, you get pressure differences and density difference and pressure differences that creates wind aloft. So in the upper part of the troposphere, you get these winds that we call jet streams. We hear the most about this one, the polar jet stream, and they flow from west to east. This is deflected. We'll talk more about this in a second, but they're deflected and they flow generally from west to east. So the jet streams are like these boundaries between the major air masses in each hemisphere. This is, direct from the National Oceanic and Atmospheric Association informational website. They've got a ton of information if you want to do some research on weather. But this is just kind of a stylized version of atmospheric circulation, right? You have cold air sinking, leading to higher pressure at the surface. We have warm air rising, creating lower pressure at the surface. And nature hates a vacuum, right? So the air is going to flow. The flow of air from high to low pressure, also known as wind, okay, is going to be from high to low at the surface. And then as warmer air is being lifted, it's going to flow back. Air can't just sink forever, right? So as air is sinking, it needs to be replaced from aloft. The final piece I haven't really mentioned yet here is this rotational aspect that high and low pressure systems have, right? So which way do low pressure systems rotate in our hemisphere? Generally? Counterclockwise. Yeah, counterclockwise, right? So-called cyclonic rotation. Has nothing to do with the way that your toilet flushes, okay? But it has to do with this thing called the Coriolis effect, which is imparted by the fact that the Earth is a rotating frame of reference. And I could talk for an hour about the Coriolis effect, but I think for right now, it's just enough to know that in the Northern Hemisphere, the wind is deflected to the right in the Northern Hemisphere. So we can see if we have air flowing towards an area of low pressure, it's going to be deflected to its right into what's ultimately a counterclockwise pattern. So low pressure systems rotate counterclockwise in the Northern Hemisphere, and high pressure systems rotate clockwise. And then finally, these differences in pressure, right, between areas of high pressure where air is sinking, areas of low pressure where air is rising away from the surface. The differences between those, the so-called change in pressure, or the horizontal, we call the gradient, right? The difference in pressure between one area and another is what creates wind. So air in general tends to flow from areas of high pressure to areas of low pressure at the surface, and it's it's deflected by the Coriolis effect, so it's rotating. Okay, so here we have a high pressure system. General flow is clockwise. We've got a couple of active tropical cyclones in the North Atlantic right now. Isaac out in the middle of the Atlantic, and then Helene over the in the Gulf, and we can see they're both very steep pressure gradient. So this is a hiking map, right? You'd be looking at a very steep hill here, and so it's the same notation. This is today's weather map. These lines are what are called isobars, and these are just lines of equal pressure. They give you a sense of how quickly pressure is changing at the surface over the distance. So you can sort of, in general, get a sense of, the wind direction, but also the wind speed based on the spacing of these lines. But like I say, for now, the understanding that change in pressure at the surface is what gives us wind. So we'll take one more look at this drawing, right? We were just looking at this, sort of a hemispherical wind model. As we said, we have air that's flowing towards the tropics from further north. Warm air is rising up out of the tropics, being replaced at the surface. And as we now know, right, instead of just flowing from north to south, right, this air is being affected by the Coriolis effect. So it's generally turning to the right, okay? So it's going to be deflected to the right. And so which way is this wind actually going to be blowing in the tropic? From east to west, right? It's going to be blowing south, but it's going to turn to its right. So it's flowing out of the drawing towards you. So from east to west. And then in our latitudes, okay, in Maine, right? What's our general wind direction here mostly? Southwest, except when it's northwest, right? Southwest, northwest, easterly once in a while, right? But generally westerly. Okay, and that's because in our latitudes, generally, we have air that's flowing, air that's being lifted along the polar front, and generally being deflected again to its right into a westerly flow. Okay, I've got a better slide of this coming up, but if we take this diagram, we're just looking at one hemisphere now, but if we zoom out, okay, here's the whole world, right? If we look at sort of what a sailor's map of the world's winds would look like, so we were just talking about, right, in the tropics where we have an area of sort of continuous low pressure with wind pretty much flowing continuously in that direction towards this area of, just sort of stable or continuous low pressure right along the equator, right at the heart of the tropics with winds flowing in from either hemisphere. These are the trade winds. These are easterly winds that are deflected by the Coriolis effect in each hemisphere. And so, right around the tropics. And if you've been there, right, you know this, right? Whether you've been sailing or just down there noticing that like the trees all lean in the same direction and the wind always blows the same way all the time. So these are the trade winds, while as in the higher latitudes, okay, sort of up where we are, the predominant wind patterns are westerly. Okay, as we'll see in a minute, sometimes they're southwesterly, sometimes they're northwesterly. Occasionally we get an easterly wind, but for the most part, you sort of think about this from the standpoint of a sailor, right? And it's, can already get a sense if you're, traveling under sail. If you're going west, the going is easier in the tropics. If you're going east, the going is going to be easier sort of in the higher latitudes. I think a good way to look at that, if we look at the way some of the, the world's traditional sailing cultures got around, let's take a look at the first Europeans. As far as anybody knows, the first Europeans to get to North America were not, in fact, the Spanish and the Portuguese, not Columbus and that crew. Were probably the so-called Vikings, right? The Norse navigators, sometime around 1000 AD. So, 400 or 500 years before the Southern Europeans got to the West Indies. There's at least one confirmed Norse settlement in North America at the northern tip of Newfoundland, and evidence that they are elsewhere. And, there's also written records of voyages back and forth across the North Atlantic to, Iceland, Greenland, and then again, at least once as far as a place called Vinland, which is, pretty conclusively the east coast of North America. So how did they do this? Well, sort of think about, the weather in our latitudes, okay, is dominated by mixing of warm and cold air along this feature that I call the polar front. This is a, satellite photo. I drew these these lines in the sort of crayon lines I drew in, but it's just a satellite photo of a fairly standard North Atlantic low pressure system. And what's happening here, we have cold air that's pushing down from the Arctic. We have warm air from the middle latitudes and the tropics that's being lifted up over the cold air, sinking down out of the Arctic. And as the warm air lifts, right, the pressure at the surface drops, draws in more warm air. The cold air, the cold dense air sinks in behind it. And because of the Coriolis effect, this whole system, we're looking at a low pressure system with a counterclockwise rotational aspect. So you think about if you're in Northern Europe, right, and you want to get to North America, where do you want to be? Okay, somewhere north, right, on the north side of one of these systems, okay, where the wind is generally out of the east, okay, when the time comes to go home. Okay, better off to get to the south, right, on the southern side of these low pressure systems. The wind is on the south side of the system is generally going to be out of the southwest, so they're sometimes called the warm quadrant of the system. And then here on the back side of the system, it's going to be where the cold air is advancing into the system, is going to be out of the northwest. And we see this all the time here, right? We have a continuous view of these systems that go by. In fact, right now, right, so warmer version, right, it'll get a lot colder in the winter, but right now we have winds out of the south and a lot of clouds and precipitation. Sometime over the next day or two, we'll probably see a bunch of sort of, wind and rain activity, and then, on towards the weekend, right, things will clear off, and that will be the cold front that we've seen, this boundary, this cold density boundary between cold, dry air and the warm, moist air. So this was traditionally, right, the sailors of the North Atlantic, at least, the first transit from Europe to North America was almost certainly made with a pretty thorough knowledge of these systems, right? The Vikings were in North America for at least 100 years, at least as far as the archaeological record shows, and pretty good evidence that they were able to get back and forth. So if you're in the tropics, okay, sailing is characterized by sort of more consistent conditions, right? In the tropics, they're actually, with one major exception, there aren't really a lot of weather systems, right? You get the trade winds, which is just this consistent circulation of wind sort of towards the warmest part of the tropics, towards the heart of the tropics, converging from both hemispheres and being deflected by the Coriolis effect into the easterly trade winds. So the wind blows very consistently to the east, and sort of day to day, it can get a little monotonous, truthfully, right? Day to day, the wind blows consistently from the same direction, and the atmosphere is pretty much always warm and moist. There's a tremendous amount of evaporation off the oceans. A lot of cloud development as that warm, moist air is lifted and cooled off. So you see a lot of these cumulus clouds. And the one exception here, right, as I was saying, in the tropics, really the only type of systemic weather we get in the tropics are tropical cyclones, or which in its extreme form can be a hurricane. But a tropical cyclone is a low pressure system, okay? But instead of being composed of different air masses, instead of being developed from the mixing of warm and cold air, in a tropical low pressure system, a tropical cyclone is just an area where the atmosphere has become very, very warm, very, very moist. And as it rises, right, it lifts that moisture up into the atmosphere. The water vapor condenses into liquid. It releases heat as it does so. And if there's enough heat and enough moisture, this can become kind of a self-generating system. Okay, so in the warmest time of the year in each ocean, so-called cyclone season, right? There's an incidence, that varies from year to year, right? But the development of low pressure systems, very intense low pressure systems, will sometimes develop all the way into hurricanes. But just somebody asks you, like, what's the difference between a tropical low pressure system and the type of low pressure systems we generally get here? Here, most of our weather systems involve the mixing of warm and cold air, cold polar air, warm air from middle latitudes. In the tropics, right, they're just very, very energetic examples of something like a thunderstorm, where you get warm, moist air that's been lifted off the surface. It pulls more air in at the surface. And again, in the tropics, there's so much heat, there's so much moisture available. This process can, propagate and sort of build through its own momentum, sort of continuous processing of warm, moist tropical air at the surface. So we call them hurricanes in the North Atlantic. But, globally, these storms have different names, but they all, tropical storms all form through the same mechanism. You can kind of see, right, the hurricane or tropical cyclone seasons tend to coincide with the warmest time of the year, the sort of heating maximum. So, the North Atlantic hurricanes kind of June through November. Typhoons, okay, so the same thing. A typhoon is just the Northern Pacific name for a hurricane, and they happen at roughly the same time of year, right? June through December. And then the Western Pacific and Indian Ocean, they just call them cyclones, but it's the same. These are tropical cyclones. Kind of interesting, the Eastern Pacific, Eastern South Pacific, and the Eastern Atlantic, and a lot of the South Atlantic actually don't see much of this kind of thing at all. And that has to do primarily with the fact the water is much colder on this side of the ocean. On the east side of ocean basins, the water in general is quite a bit colder. And so it's not warm enough to support tropical cyclone development most of the time.
Excuse me,
Yeah.
is that because the Earth is turning toward the east and it's actually leaving the warm water behind?
It does have to do with the rotational momentum of the Earth, right? And what happens is that the oceans themselves have a current circulation. Like each ocean basin, right, has a rotary current circulation, and what that does is it tends to, on the eastern side of the basin, it's because of the rotation of the Earth, right? It's also induced by the Coriolis effect, but because of those rotations, the current tends to bring warm water down out of the tropics on the western side and brings cold water up out of the poles on the east side. Exactly, right. So you think about like the North Atlantic, our main ocean current system is, it's the North Atlantic gyre. We think of it as the Gulf Stream as the western boundary, right? And that's a warm current up out of the tropics. But the other part of that rotation is a cold current that comes down out of the higher latitudes. So,
Thank you.
yeah. But it's definitely down to rotation as one step further in terms of cause and effect. So we look at tropical voyaging, looking at historical voyages, right? The first tropical voyages from Europe were taken by Columbus and his contemporaries 400 or 500 years after the Norse navigators, and it was pretty well established in Southern Europe. They were familiar with the trade winds, right? They were sort of locally familiar with them. But kind of the crux discovery, really, you could sail west from the trade winds very easily, but somebody needed to figure out how to get back, how to get home again. And that was kind of the crux discovery, this thing they called the Volta do Mar, which is Portuguese for return from sea. And it was this basically this recognition that if you're sailing west from the trade winds, their ships look kind of like this, right? So I think there's some sailors in the room would recognize this isn't what you want really if you're trying to sail to windward, okay? It was eventually discovered, probably in part by trial and error, that if sailing west, if you wanted to sail east again, you could sail north, okay, and eventually find your way into the westerlies, sort of the lower side of the North Atlantic cyclones, right? They could find themselves into the westerlies and sail back again. And so that was actually the first place they discovered doing that was the Azores, okay, and then eventually that was the technique that Columbus and his successors used for getting successfully might be the wrong word, to some of the people who are already living there, but were able to get back to Europe after traveling to America. And that's also so sort of think about that as a technological leap, which it really was, right? This recognition that you could get out of the tropics and sail back the other way in an ocean basin. It's a little bit like in the book, I kind of call it, compare it to splitting the atom, because it really did in terms of like the European population being able to get around the world under sail. Right around the same time as Columbus was, what they were really trying to do is find a sailing route to India, right? To the East Indies, which actually I think Columbus died thinking he had succeeded in doing. But at any rate, Columbus's contemporary, some of the other, well-known explorers of that era, like Vasco da Gama, right? Vasco da Gama was the first expedition leader who actually successfully sailed from Western Europe to India. And the bet that he made successfully, or that his navigator made successfully, was that this system of trade winds, easterly winds in the tropics and westerly winds in the higher latitudes, would hold true in every ocean basin. That's sort of the gamble that they took. And it was true, right? They found that in the South Atlantic, just like in the North Atlantic, right? If you wanted to go east, if you got into higher latitudes, right, you could sail from west to east. Okay, and then when they got into the Indian Ocean, it's interesting, the Indian Ocean is dominated by this thing called the monsoon, which is kind of like a seasonal version of the sea breeze that we're very used to here in Penobscot Bay, right? You got up in the morning, and there's no breeze, and then by 1 o'clock in the afternoon, the summertime, you get a nice breeze off the water, and that's because the land heats up, and you get colder air off the water flowing in. The pressure drops over the land and is warmer over the water. So it's pretty typical, and then at night things cool off and it quits. There's a seasonal version of this called the monsoon that happens in different parts of the world. So in the summertime, right, the Asian continent heats up, and an area of low pressure develops over the land, and you get a sea breeze blowing in off the Indian Ocean. And then in the wintertime, as Asia cools off, the air is very, very cold, and so it switches over into an offshore breeze. And kind of understanding that back and forth was kind of the key to the last step of getting from East Africa to India. There was a well-established culture of navigation already in the Indian Ocean that went back several thousand years that was based on that, right? There were many under sail across the Indian Ocean based on an understanding of the monsoon. It was basically through kind of leveraging that, right? The Europeans needed to learn how that works, however they found it out from the locals. And actually, the process of carrying cargo under sail in the Indian Ocean lasted just about as long, interestingly enough, as it did in the like when you think about cargo under sail on this coast, right? Schooners carrying coastal cargo. Mid-20th century, right up until about the time of World War II, there was a pretty active commercial sail industry. Talk about the Polynesians, although the Polynesians were actually one of a series of, very accomplished open ocean voyaging cultures that settled the Pacific. And in fact, right, by the time that, the Europeans got to the Pacific, that was Magellan's circumnavigation in the early 1500s. And by the time the Europeans got to the Pacific, like if you look at a map of the Pacific, right, what do you mostly see? Mostly water, right? Okay, but if you get really close, right, if you have a magnifying glass or you've got it's actually covered with islands, and every one of those islands has a population on it that was there, that was settled before, the Europeans even before they even knew the Pacific existed. And some of them quite old, right? Some of the islands in the sort of Western Central Pacific, places like Samoa, Tonga, places like that. At least 3,000 years ago, people figured there were populations that had made their way there, sort of starting in the archipelago of Southeast Asia, and then gradually from island to island, traveling in, sailing canoes. They don't look much like canoes we have, but these are large, multi-hulled, open or semi-open boats. The interesting thing about this is we're in the tropics here, so the prevailing winds are generally easterly, but the spread of settlement in the Pacific generally went from west to east. So that sort of speaks to a fairly sophisticated, again, understanding of the wind patterns. It's not always out of the east. It's just most of the time there are variations connected to things like climate patterns, things like El Nino, tropical cyclones, and so they were able to over time. And again, this was not like one person in a canoe who got lucky, right? This was a millennial, hundreds and hundreds, thousands of years, repeated voyages back and forth, all the major archipelagos of the Pacific, right? So there are just things like DNA records and for archaeological records and things like that. It's pretty clear that people were going back and forth. Hawaii was settled just about 1,000 years ago, right around the same time as New Zealand, to sort of the last major land masses in the Pacific to be settled. And maybe they may have gotten as far east as the west coast of South America. That at least has not been disproven.
Question.
Yeah.
What compelled them to go to sea and look for an island? I mean, you're out there, there's nothing out.
Yeah. Yeah.
And are you just going to sail until you find a piece of land or what?
Yeah.
And then sail back and tell your people that you found Hawaii or?
To a certain extent, I think, yes. I mean, there are enough islands distributed that I think there was, based on a successful history of exploration and expansion, But there's no, I mean, there's no real written records. Certainly ethnically, the populations are all still there, but there's not a well-preserved written history. They've done a pretty good job over the last, say, half century, to recover some of the navigational techniques. So there's, working on a, sort of rebuilding and understanding of how they actually got from place to place. But the sort of why, and these weren't, like I say, I mean, I figured there were probably about 1 million people living on Tahiti when Captain Cook got there. Right, so these were not just small outposts.
Those dates are debatable and it wasn't, I mean, it's like going beyond the horizon instead of recalling in a lot of cases. And also I'll say that Easter Island, they just did a recent test on the DNA of the people and they found connection with South America.
Yep.
It's always more to explore.
Yeah, exactly. Right. So, and just suffice to say that, and you hear a lot about the Polynesians, but they're one of, 3 or 4 very accomplished sailing cultures that had populated the whole Pacific, probably 400 or 500 years before the Europeans even knew it existed. Sort of the final evolution of, commercial sail in a global sense, like with the so-called clipper ship routes that took advantage of the very strong westerlies in the Southern Ocean, right? The so-called, roaring 40s and furious 50s and screaming 60s. But anyway, we're sort of in the, high middle latitudes, right? So the wind is generally westerly. And here in the so-called Southern Ocean, right, there's no land in the way. So the wind can blow very hard without much interruption. Easy, probably nothing easy about it except to say that, if you're trying to sail around the world, if you didn't mind sailing east in very heavy weather conditions, at least for a period of time, right, 50 or 75 years or so, they built ships that were up to it and sort of the commercial sailing routes generally, right, there were, all kinds of things going on, but in general, right, from Western Europe, south into the Southern Ocean, and then generally from west east to pick up. These were bulk cargoes, things like grain and nitrates, fertilizer and things like that. And then typically, east around, so they would sail, continuously, just keep sailing east back around Cape Horn, and back up to Northern Europe. And these are still the routes that are taken advantage of by the, sort of modern, high performance, around the world competitive sailors. The traditional, the commercial ships set a lot of records that, for passages that have mostly been broken at this point, but it's impressive how long many of them stayed around, right? You look at boats that are built to sail fast, and these are ships carrying thousands of tons of cargo, and putting in some pretty astonishing sailing performances.
We just read the book The Wager about sailing under South America and trying to get into the Pacific.
Are they trying to go from east to west?
Well, they didn't make it.
Okay,
And,
yeah, okay. That's on the stack of books in my living room. I haven't read yet.
But why would you even think to go that way? I guess because it's longer, but.
Yeah, I mean, there was certainly, there were like, if you were trying to sail from New York to San Francisco, right? I mean, there were a lot of ships that did go around Cape Horn from east to
That's
west,
true.
but it was a very, and that was how Magellan did it, right? But it was, never easy, right? And, those tended to be, much longer. I mean, ships would wait sometimes for months to get a fair breeze to get around Cape Horn. These are sailing routes. So this is data from 1990 to the present. All from sailing vessels. So pretty much this is sort of into the era where, sailing vessels could report their position by satellite. I think these data are mostly connected to this technology called Inmarsat-C, which is at this point, fairly simple, it's easy to say, but satellite communications technology widely used in the sailing industry. So these are where the sailboats go now, right? So we're looking at the last, 30, 35 years. And so this time I can tell you what the colors mean. Okay, so blue are the boats going west. Okay, and green are the vessels going east. Okay, and red is north and south. And you can see, pretty consistently, right? If you're going west, you want to be in the tropics. Okay, either northern hemisphere, boats coming out of Western Europe, the Med, Canary Islands, probably right about here, and then pretty much a blue highway, right, from the Canary Islands to the Caribbean. North, south, there's Bermuda right there. I bet relatively easy to go from north to south. The north-south routes are pretty much defined by where the waypoints are, right? Here's Hawaii, here's Bermuda. But then you can see from from west to east, okay, generally in the higher latitudes. There's very, very few people, you might even say nobody, right, trying to sail from west to east in the tropics or from east to west in the higher latitudes. If you wanted to go east to west, right, you get into very high latitudes, right, where the winds are more generally easterly. But you know, there it's cold, right? Who wants to do that? Okay, so now climate. I think I've left enough time to talk about this. So this is a map from the Climate Change Institute at the University of Maine. Just looking at how the oceans. I suspect many of you have seen graphics like this before, but just sort of talking about how much things have warmed up in the last several decades, right? And what the map is really showing, it's looking at a 20-year period, roughly like 2005 to 2021. Compared to the preceding 20-year period. And what the colors mean are changes in average temperature since that time. The higher latitudes, right? The average temperatures are as much as 4 or 5 degrees warmer particularly in the Arctic, than they are anywhere else on Earth. There's some places that have stayed more or less steady. Kind of an interesting here, it's Southern Ocean surface temperatures are actually on average colder. But Antarctica, again, much warmer over the last 20 years, and pretty much all the rest of the terrestrial surface of the Earth the same. So these are the facts, right? So we're just finishing up the warmest year in recorded history, and actually all of the last 15 years, and nearly all the last 15 years have been the warmest in recorded history. And most of that excess heat is absorbed by the oceans. The oceans are a much more efficient absorber of heat energy than terrain is. So all that heat's going into the oceans to the point that the mean sea surface temperature. Okay, so this is scientific data here. Okay, from NOAA, but the mean sea surface temperature is almost a full degree Celsius warmer than it was 100 years ago, and that doesn't sound like that much, right? But it's a tremendous amount of energy, and like even scientists who are fairly sober people, start talking about like atomic bombs per second. The rate of energy that the oceans have been absorbing, and what some of the results of that are, right? We're talking about, well, how has this affected weather, in particular weather for mariners, there's because heat is responsible for evaporating water vapor off the oceans, or evaporating water off the oceans. There's about 6% more water vapor in the atmosphere now, okay, than there was 100 years ago. It actually just ran across this acronym the other day. They were talking about a couple of weeks ago, North Carolina had some sort of record rainfall. We seem to hear about this kind of stuff quite a bit. There's a thing called WAP, okay? And WAP means water available for precipitation. So that's water vapor that's waiting in the atmosphere to make rain. Connected to that, okay, and this is data from a scientist who leads a team down at MIT named Kerry Emanuel. Thermodynamically, what that means is that tropical cyclones, okay, have enough additional energy because of that water vapor that the sort of theoretical maximum. So this we're talking about how strong a tropical cyclone has the potential to get, has increased by about 25 knots. Okay, the theoretical maximum speed of tropical cyclones. And then finally, okay, because the poles are warming so much faster, okay, the global climate zones sort of if we look again at this image, right, we think about, circulation globally is really driven by the fact that you get very sharp differences in temperature between different parts of the atmosphere by latitude, right? So as I said, the poles are very, very cold. The air is very, very dense. The tropics are very, very warm. The atmosphere is much less dense, and that sort of sets up this sort of established system of circulation that we're used to and the weather that's connected to it. But as the poles warm up, what's going to happen to this diagram? Okay, the difference is the gradients in temperature and pressure are going to be less pronounced. So the tropics are getting warmer and warmer and wetter, and so it's kind of easy to maybe draw a direct line from that to maybe more tropical cyclones. But the fact that the poles are getting warmer also is also going to affect the assumptions that we've been making about weather patterns. So, has anybody seen one of these before? Pilot chart? Yeah. So this is just a, navigational tool, right? Basically a stored record of climate. You can use these for planning voyages. And if you're planning a voyage in the North Atlantic, here we are in September, and the pilot chart is this is something that started back in the 18th century. There was a guy named, a Navy lieutenant named Matthew Fontaine Maury who began this project and sort of continues, right? Climatological data. It's kind of like the Farmer's Almanac for mariners, right? This is data about, month by month, what the climate trends are going to be in a given piece of atmosphere. And so you can look at this, and particularly if you're sort of sitting in the front row, I'm just going to tell you that, the wind direction, right? For each grid square is going to be pretty consistently from the east to the northeast in the tropics and pretty consistently from the west in the middle latitudes. It can tell you, month by month where you can expect to find icebergs, how likely you are to encounter a tropical cyclone. So these are baselines that have been established, for over long periods of climate measurements. The thing is, right, we just talked about how things are changing, right? The climate boundaries aren't where they were. How are global weather patterns changing? Has anybody heard of somebody named Jimmy Cornell? I know I was having a conversation with one of you about that before the show. So I think the answer is yes from at least one of you, but he's Jimmy Cornell, right? Very accomplished cruising sailor, has written a lot about, different sailing routes around the globe. And he's done a lot of work on using these same tools, right? Looking at pilot charts, looking at the established pilot charts and actually making some revised versions of his own. He's actually got a great book of his own. It's called The Ocean Atlas. He's actually, this edition is now, it's good for the coffee table, but now, as he indicates, it's kind of obsolete. This is 2011. This is the first edition. I think he's now on his third edition. And what he's finding is that the sort of global wind patterns that cruising sailors count on, the wind still blows, right? But the established patterns are actually noticeably different, at least by observation. The most significant consequence of that that he's observed is this: the trade winds, right? These are very reliable, very strong easterly winds in the tropics. Appear not to be as well established and as reliable in the past. And you would think, well, that would kind of follow, right? Not being a scientist, right? That would kind of follow, right? The trade winds are really driven by the fact that the tropics are much warmer than anywhere else on Earth. And if that difference is diminishing, right, then things like the trade winds are going to be less pronounced. And that appears to be the case. At the same time, it also appears to be the case that we're getting more tropical cyclones, right? The fact that the oceans are warmer, the atmosphere is warmer, there's more water vapor in the atmosphere. So this is 2020, so just a few years ago, it was a record season for tropical cyclones. There were 30 storms, right? We were all around to see it, right? So this is a record year, but the following year wasn't. And what we'll see is like the following years have been no slouch either. This is some data on the occurrence of tropical cyclones in the North Atlantic. And what this looks at is the occurrence of the strongest cyclones, so category 4 and 5 hurricanes. So with wind speeds above 115 knots. This is 2000, year 2000. This is 2020. And we've gone from an average of, a little more than one, like these are the major hurricanes, right? With winds above 115 knots. We've gone from on average, a little more than one to a little more than two, right? So a doubling in the number of the most powerful tropical cyclone. So that was 2020. There's 2021. Okay. Here is 2022. Okay, what we find actually, right, is again another statistical table. This is 9 years, again from NOAA, 9 record Atlantic hurricane seasons. And what we see is of these 9, right, 7 of them have happened since 1995, right? So we got 1995, 2010, 2011, 2005, 2020. So, all the last 9 or 10 record North Atlantic hurricane years have all been in the last few decades. Okay, and again, we can see here 2020, there were 30 storms, 2021, 21 storms. Okay, 2020 was one of those years when they actually ran out of names and started having to give them letters. Let's remember that or not. Okay, as we can see, right, this is, well, this is today, okay, and so we can see after kind of a quiet period, in which I read that the forecasters were actually starting to worry about their credibility, which is kind of a funny thing to be worried about, but, okay, so this is now, right, we can see that, after a year of predicting this would be a very active hurricane year, there wasn't a lot going on for a while, but now we've got two active tropical cyclones in another area that they're watching very closely, and right, as we're, talking about, before I got started, right, Helene is in the Gulf and, forecast to impact the west coast of Florida, probably right about now.
Elliot?
Yeah,
What I'm seeing this year is most of the cyclones are building in the tropics and then turning north before they get very far west. There are a lot of cyclones that are going up the middle of the ocean.
yeah, you'll have to ask a hurricane forecaster about that.
Seems like which,
So I think in the case of Helene, right, that's a storm that's, looking at some of the data from Helene, right, Helene was not well organized kind of in the Western Caribbean, actually, organized and intensified, quite quickly as it got into the sort of Gulf of Mexico, right, and moved up to sort of the warmest area. The warmest water in the North Atlantic is right about here. There's this thing called the loop current, which is just sort of a jet of warm water that makes its way up into the Gulf. So Helene and there've been a couple of storms this year that actually done this that have intensified very quickly, just sort of right over the Gulf of Mexico, moving into that very, very warm water and warm air. And you can actually, this is a forecast from yesterday, but you can see the H and then the M is major hurricane. So you can see intensifying, very quickly from just a gale into a major hurricane over a very short distance, very short interval of time.
That Western Caribbean has actually gotten more developed that way.
Yep.
In the recent years. The feeding ground.
Okay, and then this is again this forecast. So, and this is right about now. But the point being just that they're seeing seem to be seeing a greater incidence of storms that of tropical storms that develop and intensify very, very quickly. So I'll just end by talking about, the other sort of major weather engine in the hemisphere, right, is this what I was talking about before, this very strong difference between sort of the warmer air in the middle of the globe and the colder air at the poles. That's what gives us the so-called jet stream, right? These boundaries are marked by these strong currents of westerly wind. And in general, like these form pretty much a delineation, right, between the colder polar air and the warmer air near the subtropics. And as long as that difference is very sharp, right, the jet streams are fairly powerful. What happens is as the sort of thermal difference between the tropics and the poles becomes less pronounced, the jet streams themselves, what they're observing is they're less energetic and sort of more meandering, right? So that's sort of what leads us into things like we think about these, sort of abrupt outbreaks of weather that then tends to stay around for a while. And I'm just about run through the time that I want to talk. I'd like to take some other questions, but so let's look at some examples of that, right? So here's kind of a cartoon of the jet stream, right? And a generally pronounced current of west to east wind. And this is not a surface wind, it's up around right up around 20,000 feet, we'll say. Very cold polar air on one side and sort of milder subtropical air on the other side. And as long as this temperature difference is very strong, the wind itself, the jet stream stays fairly strong. But as the poles warm up, the jet streams they get slower and they become more meandering. And we get into these situations where you get an area of warm air that pushes north up into very high latitudes and pushes the jet stream meanders around it and carries cold air further south than we're accustomed to seeing it, right? And you run across different names for this. Sometimes they talk about it's a little hard to sort out the terminology sometimes, but we'll talk about like an Arctic outbreak or something like that. And what's really happened there is you've gotten warm air that's pushed its way up into the high latitudes and displaced cold air further south. And so you get these swerves in the jet stream. And once it meanders like this, these features take a while to go away. Okay. And these sort of tongues of cold air pushing down into the warmer parts of the planet tend to trigger outbreaks of severe weather sort of at the surface. So we'll look at a couple of examples of this. This is kind of a real time. This is an actual feature. It's a few years ago, but this is a typhoon in the Pacific, so a tropical storm that carried a lot of warm air. Here's Alaska here that carried a lot of warm air up into sort of Western Canada and pushed this big jet of cold air down over the U.S. continent and triggered a very strong outbreak of severe weather sort of over the continent in the fall, severe fall weather. But we can look at examples of this more locally. Well, this isn't really local, but this just happened. A couple of weeks ago, Western Europe, right, had a catastrophic rain event, world record rain event. This is actually in Czechoslovakia. I think it's flood, but it was a case where, again, a very strong intrusion of warm air from the African continent up into the higher latitudes of sort of Central Europe and Western Asia, and a very strong meander in the jet stream and cold air pushing down. Kind of overall, reaching all the way down to the Med, and the boundary between that very cold polar air and very warm, very warm, humid Mediterranean air triggered a series of storm events over Western Europe that just dumped a ton of rain. Right, this was just a couple of weeks ago. If you saw it on the news. Oops, going the wrong way here. Last winter, okay, here we are back at home. Okay, last January, we had not one but two severe coastal storms. What was the cause of that? Well, it was actually, again, it was a case where the jet stream, we had a and these aren't unheard of, right, in the wintertime, where the jet stream makes its way, very far south of the North American continent. But in this case, it was partly triggered by the fact that kind of over on the other side of the globe, there was a large mass of warm air over East Asia, right? There were record warm temperatures over Siberia, Japan, things like that. And that deflected the jet stream down over the North American continent, where it sort of stayed, right? This pattern took a long time to dissipate. And the result of that, right? And probably many of us were here to see this last January. We had, not one hurricane strength coastal storm. These are weather maps, okay? So I'm going to click to this next weather map, and this looks like exactly the same map, doesn't it? But it's not. Okay, so these were two sort of hurricane strength coastal storms that we had last winter, and they were both the product of a large sort of southern outbreak of the jet stream over the continent. So these are two separate storms that spawned by the same sort of larger systemic feature. So this is the kind of stuff we go looking for. We talk about well, how is climate change affecting weather? I think, like I say, as mariners, right, and the day-to-day sense, you're sort of caught up in the day-to-day. So it's really hard to draw a line between events that you could really call climate science. But it's the science is there in the background to explain the sort of apparent occurrence of more frequent severe weather, more tropical cyclones, more repeated severe weather events in the higher latitudes. I'm about out of time. I'd like to leave some time for questions. But other things, another interesting thing to talk about would be like polar navigation, right? There's, there are now commercial sailing routes in the Arctic, right? Places that were impassable to shipping 20 or 30 years ago with all sorts of connected consequences. As weather patterns move around, another thing we talk only briefly about is there's a tremendous amount of cargo that gets carried on inland rivers, right? And what the rivers need, well, they need water, right? And as rain patterns move around, what we're finding is navigational patterns on all sorts of waterways are getting disrupted by that. So, the rain is falling, right? But it's falling in some cases in record quantities, but in other places not as reliably. Last summer, the Panama Canal had to reduce operations, basically because they were running out of water, right? The way the Panama Canal works is they drain water out of the big lake that's in the center of Panama. And that's been reliably filled up by tropical rain for as long as anybody can remember. But last year, no, right? They had basically drought conditions and had to restrict ship traffic in the Panama Canal. So I said I'd leave time for questions, so I'm going to wrap up there. But thank you very much.
So these collapsing jet streams are carrying warm air very high in the latitudes. That's not the main reason why the Arctic is getting warmer, is it? That's a separate.
No, that's right. Yeah, the Arctic is getting warmer primarily because as temperatures increase, across the board. There's less and less sea ice in the Arctic, and as things get warmer, there's less sea ice in the Arctic, and the more open water there is, the more energy is absorbed into the ocean. You know, ice is a very good reflector of energy,
Right.
so with less ice, the
At the
poles are.
start of that process,
Yeah.
which led to the ice melting, was that, I mean, what's
I
the?
think that's down to general warming, right? So, general warming of the atmosphere, greater concentrations of greenhouse gases. But that's turned into, the scientists like to call like a positive feedback
Right.
cycle, right? Where things get warmer, there's less ice. The less with more open sea surface, the ocean warms more quickly. So year on year, progressively there's, they're losing like, an area of sea ice about the size of the state of Maine each year, effectively being subtracted. Pattern.
Right, the other major aspect of that is the snow. And the tundra doesn't have snow, all of a sudden it's a dark surface instead of a light surface.
Right.
And it absorbs a lot for heat.
Right, exactly, right. So all the reflective surfaces are being replaced by absorptive surfaces, yeah.
And that warming would actually contribute to the jet stream leveling out, where most of the last winter was pretty mild. Because there wasn't that differential between the cold above and the warm below. But when the cycle jet stream does a big whoopie-doo, when it's thrown off that, then you get more frontal storms coming through.
Right, yeah, and typically, situations like that, if you got, a cold outbreak, you can usually trace that to a warm outbreak somewhere else, somewhere else on the surface, right at the same latitude, warm air pushing its way up into the higher latitudes.
Elliot, can you speak a little bit about, as a mariner, how this affects you and personally in your voyages, your planning and?
Yeah, I would preface that by saying I'm still spending some time at sea, although not doing as much voyage planning as I did when I was sailing full time, at least for now. I think that, like I say, in general, things like, planning routes, particularly for, smaller non-commercial vessels and things like that, the definition of things like cyclone seasons, and, when you think about the boundaries of cyclone seasons and when you would plan like a north to south passage in the North Atlantic. I'm not working on inland waterway or something like that, so I haven't been affected by things, by the changes I was describing very briefly. So like I say, in a sort of day to day, it's a challenge for all of us, right? We're all caught up in our day to day getting things done, so it's difficult to identify trends in a definitive sort of way. Yeah. Yeah.
Great talk. And just in case nobody else says it, I highly recommend your book.
Oh, thank you. Thank you very much.
Don't read it at time.
Sorry. Yeah, I was trying to make it interesting.
There is this interesting scenario where the Gulf Stream basically, since it's the functions that it has, and Northern Europe gets colder rather than warmer.
Yeah,
Which
yeah,
is.
yeah, because right now, Northern Europe is kept warm by that steady supply of warm water in the Gulf Stream. And that's all I saw, like the most recent round of measurements, if they haven't been able to identify that yet, although certainly, there's certainly one model, or there are models that indicate that could be an outcome, but.
I'm curious about, when you've been sailing, when the weather patterns that you thought you had mapped out and knew, you were totally surprised, and what was the outcome?
Well, I think I've been on a couple of trips, sailing trips where, like, east to west passages in the North Atlantic where we, sort of expected to have, and the trade winds are a pretty good example, right? You sort of, get yourself into the tropics and pretty much be able to count on sailing west and making good time. And I've been involved in a couple of trips where, they just didn't show up. Actually, Atlantic and a couple of Pacific trips also, where just that sort of, the trade wind, it was not catastrophic, but cases where it was, in the Pacific, it had to do with, it was a sort of El Nino cycle thing, I think was as much to blame as anything else, but, where you sort of count on prevailing winds, for a passage and you either wind up without them or actually with winds from the other direction. Yeah.
See, there's a lot of fluctuations even in simple patterns, which can change, like trade winds never steady
Right,
totally.
right,
They'll
right.
fluctuate,
Right,
they'll get
right.
reinforced and
Right,
die
right,
down.
right.
Same thing with other dynamics. And
Right,
other-
right, yeah, yeah, it's not a highway, right, yeah.
So that can kind of shift globally with the change in global warming somewhat. The patterns can kind of tweak.
Right,
get a little
right,
wetter.
right, so they may still be happening, but not in the established, not, where you're customarily used to finding them.
You get into that more in your book or what?
Somewhat, yeah, there is a sort of a chapter on climate, a lot of the book is sort of explanations of weather coupled to, sort of sailing examples.
And eventually mariners always come back to the shore. Hopefully,
One way or another. Successful ones do.
observations on how that shore is.
Just in terms of coastlines,
Harbors, moorings, that sort of thing.
well, last winter I stood with my father in his front yard and watched the dock in Blue Hill get, blown away. Coastal damage to coastal infrastructure. I think over in Castine, right, and maybe this isn't what you're asking, but Castine, I'm watching them build the new pier, the new training ship, and it really looks like an on-ramp for a highway, right? The dock is gonna be the highest thing in Castine.
I was thinking more of major harbors, areas like Newport, Virginia.
I think on a first-hand sense, I don't have a lot to offer, but just recognizing that a lot of the sort of sort of infrastructure, harbor infrastructure, things like breakwaters and things like that, all the stuff that's there to at least all the built environment and some of the natural environment that creates harbors is obviously no longer acting the way that it was. The sea levels and the higher tides get more and more prevalent, things like that. And some of the oldest.
The house moving industry is going to be doing well.
So my understanding, I wasn't here for the storm on the 13th, but my understanding was there was a full moon, a king tide, and then a hurricane-like storm, like all at once.
Yep.
The perfect storm, as I
Right.
say. What are the chances of those three things happening again in the next 100 years? I mean,
Zero, right?
here, are we looking at 50%, 60%, or are we looking at 10? 5?
Yeah, I don't know.
Every time,
Yeah.
every time they have a once in 100-year storm, they have another one very shortly thereafter.
Yeah, you can't say, I'm glad that I don't own shorefront property, but, yeah.
There's something on that.
Yeah.
I think NOAA has come out with something that said if we had the same conditions that we had on January 10th in 2050, the surge instead of the maximum surge on January 10th was about 8 feet. To be 14-foot surge.
Right, so the sea level, so in that sense, right, the sea level is, rising at different rates in different places, but certainly the coastal environment is gonna be less and less tolerant, less and less able to absorb those impacts.
Yeah, I'm just wondering what the, prospect is of another storm like that.
Yeah.
That was pretty unusual.
Yeah, unusual, but not, there was another one 2 days later, I know that was kind of 3 days later.
Read the paper headlines tomorrow morning. Unusual.
But, I guess, I've, sort of, lived in this part of the world my whole life, and I guess think of 4 or 5 events like that, right?
What it used to be.
In light of these changing conditions and as you say, non-zero expectancy,
Future
and
stuff.
MMA, what does that mean for the curriculum in terms of training future people be out on the sea and dealing with this? Have you noticed changes in the curriculum and is there greater sensitivity to climate change? And how's that play out?
It's sort of in a lot of different ways. When you talk about things like meteorology and weather routing, recognizing that some of the old baseline tools, right? The old climatological tools for weather routing are now being revised. Of course, we've got a lot more tools for understanding, in real time what the atmosphere is doing. And I know there's a lot being done one of the most significant things that's going on in the shipping industry is this gradual trend towards, emissions from ships, right? A long way to go, but there's definitely, definite progress in the industries towards, ship power plants. I mean, right now, ships are some of the worst offenders in terms of, ship exhaust and marine pollution and, so they're looking at.
Solar freighters are there now. I heard there's one fleet, solar freighters or wind-driven freighters.
Yeah, and I think probably truthfully, they'll be looking at just, probably not so many solar ships, but, they're looking at things like ammonia, fuel cell power plants and things like that. So there's a lot of innovation in that direction. And then just, cleaner carbon-based power plants, but, cleaner fuels and cleaner technologies for burning fuel. And then, in other places, like, I didn't, sort of ran out of time to talk about this, but, high latitude navigation, I mean, there's routes developing, in the Arctic and just kind of beginning, and sort of the US is in a lot of ways sort of way behind on that compared to, we have two polar ice breakers and neither one of them is working right now, and the Russians have 40 or 50, but the whole high latitude navigation game is really just beginning to open up, both in terms of navigation and the development of, that part of the planet, so.
Well, what did that do to the Arctic? Does it make it worse? The more,
Probably, right, I mean, the more industrial activity you have, the more ships, yeah, no question, right, so that's part of one of the questions. I'm not advocating for that, I'm just saying, yes, that's one of the questions that need to be addressed, but. Yeah, I mean, 'cause for a long time, right, that part of the planet was protected by its inaccessibility, and now it's accessible, resource rich, and, so how do those questions get addressed?
People look for that route for hundreds of years.
I know, right, now you can take a cruise, you can literally take a cruise through the Northwest Passage, you can take a
Wow.
commercial cruise ship through the Northwest Passage.
But if the route is short, that should be a good thing.
It's true, right, less fuel, yeah.
Short season.
Yes, it.
What kind of winds could we think about in the future that could be terrifying, 150-mile-an-hour storms, or what can Mother Nature do?
Yeah. I think it's examples of like more water vapor in the atmosphere, right? Warmer oceans, warmer air means, thermodynamically, right, they can figure it out, right? And, so storms, storms will have a higher potential energy. There's more,
Build their houses stronger,
I guess so.
keep the roofs on.
Yeah. Or just live in a camper, right? And just go where the weather's good. All right, thanks a lot, everybody.
thank you very much.